All right, in this video, we're going to look at how to add the sum, or the sum formula for a geometric sequence. So in previous videos, we looked at the arithmetic sum. So they are slightly different formulas. Make sure you're paying attention. So the sum of a geometric sequence means the sum, again, that means addition, of the terms up to a specified term number. So they're going to tell us, up to this term, what do they all add up to, okay? That's pretty much what they're asking us. So it is possible to compute such a term by manually adding the individual terms, although just like the arithmetic sequences, this would become difficult with larger term numbers, right? If I asked you what the 100th term, add all of the sequence numbers up to the 100th term, well, that's a lot of term numbers to not only know, but to add. There's a lot of kind of manual error that can happen there. The more manual calculations we do, the more error that happens. It's human nature. So if we can avoid doing things like that using a formula, that generally helps us make less mistakes there. So from computing the sum, which is Sn, that's what we simplify that with, or the variable we use for it, of the first n terms of a geometric sequence, we use the following formula. So we can see Sn here, so that's the sum, equals the first term, that's what A1 stands for, and then we have that multiplied by this fraction here. So the top of the fraction, the numerator, we have 1 minus the common ratio raised to the nth power, and remember n is our term number that we're looking to end on. And then we're going to divide that by 1 minus the common ratio. And remember, the common ratio, that's just the number that we multiply or divide by each time to go from term number to term number. So there may be a few things that we need to find here. We also want to keep in mind that we do have the geometric formula, just for the rule, to find the nth term. So any term that we need to find, we can use this formula, which is the first term times the common ratio times n minus 1. So using a lot of the same numbers here, but in, different ways. So we might want to keep this one in mind as well as we move forward. So let's take a look. So just like they did with the arithmetic, they're giving us a sequence and they're giving us this notation. So the first problem, we need to find the term number n, because I can see here's my first term. I can see that. And here's the term that they're asking me to go for here, but I don't necessarily see the term number right away. Now this one is a little bit nicer, excuse me, than the arithmetic sequence. Because of the way they're writing this, it's actually a little easier to find. I don't actually have to go and plug it in to that arithmetic formula or the geometric formula like I did with the arithmetic one. Because with this one, if you notice, it's 5, 5, 5, 5. If you see that, that's that first number, right? And then this -1/2, -1/2, -1/2. Well, the first number is always being multiplied by -1/2. And then if you notice, the exponent is changing, right? It goes, there's a 1 exponent here. That's why we don't see it. There's no 1/2 with an exponent here, which actually means it's 0 for the exponent. 0 exponent means 1, right? Doesn't mean 0. And then we have 2, and then the next one 3, 4, and 5. So we can actually see everything the way they have this written. So the first term is 5. We can definitely see that here. The term number is actually the exponent plus 1, because they're not counting this first one. It doesn't start counting till the second one with the exponent. So it goes 1, 2, 3, 4, 5. Well, we have that first one to deal with too, so it's actually 6. And then the common ratio, well, that's the number being multiplied each time, right? So that's that -1/2. So I immediately have everything I need to plug into my sum formula. I don't have to do anything extra for this. Now, if they didn't have it written this way, if they actually had it written as just the actual numbers instead of showing you the multiplication and the exponents, you may have to plug it into that geometric formula in order to find the term number. Because you should see the first term and you should see the last term, but you won't see the term number always if they don't have it written this way. You may not see the common ratio either. You might have to figure that out as far as, how to get from one to the other. All right, so we're going to use our sum theorem, or sum formula. We're going to add the sum up to the 6th term. So I'm going to put my first term here, and then it's 1 minus the common ratio, which is -1/2, raised to the term number, which is 6. and then 1 minus the common ratio on the bottom. So now I'm going to simplify just a little bit. So I'm going to simplify this top part here. So I have to distribute that 6th power before I can subtract. I can't do 1 minus negative 1/2 and then apply the exponent. This is only applied to the negative 1/2. So be careful about that. So I get 1 over 64. It's positive 1 over 64 because since it's 6, it's even. It's going to eliminate the negative. This negative stays, though, because that's, outside of the parentheses. That's just part of the formula here. On the bottom, I can do 1 minus negative 1/2, and I get 3/2 because it would be 1 and 1/2. But I'm going to leave it as fraction 3/2 because remember, minus negative, that turns into plus. All right, so now I can do 1 minus 1 over 64. And remember, to add fractions, you do need to make the denominators match, right? I need to make them like denominators. So 1 turns into 64 over 64, and then I can subtract 1 over 64 from it, and I get 63 64ths. Okay, so that's why I get 63 64ths. And I'm writing this sideways just to kind of save a little bit of room. If you like your fractions tall, that's fine, kind of like the way they wrote it here. I actually prefer it that way a little bit more, so you can definitely see numerator and denominator. But for space reasons, I did it sideways so that I can just, fit a little bit more on the page. So the bottom I already know is 3/2 because that was already over here. I was just simplifying the numerator. So now I can multiply by the top. Before I multiply by the top, I'm actually going to fix this problem because I'm dividing by a fraction. You can't divide a fraction, right? Anytime I have a fraction divided, I'm going to multiply by the reciprocal of the next piece, whether or not it's a fraction. If I'm even dividing by a whole number, I would flip it over, and it would be 1 over that number. But since it is a fraction, I'm just going to flip it over. It's going to be 2/3. So now you can see I've written this kind of a little bit more nice. I like the tall fractions. They're just a little bit cleaner. So now I can multiply across the top and across the bottom. So I have 5 times 63 times 2. You can do this. So I should have brought this up. I should have given myself a little note. You can simplify ahead of time, which is actually what I'm showing you there, or you can multiply the whole thing and then simplify at the end. That's totally up to you. A lot of the time, especially this far in math, simplifying ahead of time is a little easier because I can see 63 and 3. Those can cancel out. They can both divide by 3, and I'm left with 21 on the top here. 3 completely cancels out on the bottom. I can also do that with the 2 and the 64. So 2 is going to completely cancel out, and 64 is going to become 32. So now I can multiply 5 and 21, and I get 105, and then I keep 32 on the bottom. And again, Alex is leaving this as a fraction. They have not given me any instructions for rounding. In fact, it says write your answer as a fraction in the instructions. So don't turn this into a decimal. Just leave it as an improper fraction that's simplified as far as you can go. So that's the first problem here. Let's look at the second problem. So the second problem is written in what we call sigma notation. So we have this, big giant kind of funny looking E, and this E symbol is the Greek symbol for sum. Okay. The number on top of the E is the nth term. Oh, I didn't do little arrows. So that's a little 8. So 8 is our nth term. That's the term that we're going to add up to. The number below the E is the term to start. So sometimes we start with a term number other than 1, but a lot of the time we start with 1. And then the expression to the right of the E, which is right here, this 3 to the j power, that is our rule for the sequence. Okay, so now I'm going to apply the rule to find a couple pieces here. So first, use the rule to find the value of the first and the nth term. Then use the sum formula to find the sum up to the nth term. Now, you may be asking, why am I finding the 8th term when I don't actually reference that here? If I take the common ratio here to the nth term, then I'll have this r to the nth power. It actually gives me the correct number here. So that's why I'm finding this term, because I can find this very quickly and then plug it in. So you can also plug this into the formula without doing it this way for whatever reason. This is just the way I decided to go ahead and do it. So I have 3 to the first power, and I get 3. And I have 3 to the 8th power, and I get 6,561. All right, so now I'm going to take that and I'm going to plug it in to my sum formula. So I'm going to find the sum of the first 8 terms. So I'm going to multiply by my first term here, which is 3. I'm going to do 1 minus, it's r to the nth power, which is that 6,561 that we just found. So I just went ahead and did that ahead of time. And then 1 minus my common ratio, which is 3. So now I'm going to simplify. I'm going to subtract 1 on top, and I'm going to subtract 1 on the bottom, and I end up with 2 negatives. So negative 6,560 over negative 2. So now I can simplify this, right? Because both of these can be reduced, negative and negative, that becomes a positive. And also, I can divide by 2 and then multiply by 3, or I can multiply by 3 and then divide by 2. Either way, I'm going to end up with 9,840. So this is using the sum formula with a series, a sequence, and with sigma notation. I hope that helped, and I will see you in the next video.